All right, good morning, everyone. Thank you for attending this webinar. I'm Barry Burr, and I've been working with BRE for about 15 years, working on building simulations and trying to create new ways of using ProMax for different applications. And one of them that's been pretty popular lately is what we're going to talk about today. It's the caustic treating of mercaptans and LPGs. You will find certainly every refinery has got one of these types of units for removing mercaptans from some of the streams in the refinery. So that's what we're going to talk about today. We will go over a few concepts early, and then we're going to go over basically some examples. These are simulations that have already been built, and they're going to be different examples. One of them is a caustic treater that uses an extraction column, and it's similar, or basically based off of a UOP Mirox style caustic treater. And then we're going to do another one that's the other common caustic treater that we see. It is basically there's two liquid-liquid separators in countercurrent flow. That's the Mercaptan style. And then oftentimes there are vessels upstream of the caustic treaters themselves that are meant to remove any residual H2S. And we're going to go over a model of one of these that's built to dynamically simulate the spending of a caustic solution in a pre-wash vessel. So we have three simulations that are good templates, and the really, one other big aspect of this talk is to show how we can build a simulation that's very easy for you as the user to take and make very few changes and probably just enter some values through the user interface and match this system to your facility. And there's a couple of concepts I think are important for people to understand at the very beginning. When treating with caustic, generally there's some acidic species that you want to remove from a stream using caustic. And these acids vary in their own acidic strength. So the case that we're going to look at is basically mercaptan removal from a stream. And caustic is very good at removing the methyl and ethyl mercaptans out of a stream, hydrocarbon stream. Not so good at propyl, and quite poor at butyl and beyond higher carbon number mercaptans. Those are such weak acids that they don't bind very well in caustic. But generically, the mercaptans are weak acids that caustic will remove from a hydrocarbon stream. But if there are stronger acids present, those acids will eventually drop the pH of the caustic solution down to a point where the mercaptans will expel or leave the caustic and return to the hydrocarbon phase. So there's a hierarchy of acids, and these are the first ones treated. These are the order of the common refinery acids that we see and how strongly they bond with caustic. So if you have mercaptans that you would like to remove, you really don't want any other of these H2S or CO2 or SO2 present, because they're going to occupy the sodium molecules and preferentially bind to them because they're stronger acids and kick out any of the lower acids. So if you have, for instance, SO2 and a CO2 mixture, and you contact that mixture with caustic, eventually any CO2 that enters will just slip through because SO2 is occupying all of the caustic, and any additional SO2 will be picked up so long as there's still available sodiums. So just keep in mind, this is sort of the hierarchy of common refinery acids, or even some other chemical plant acids that you might treat with caustic. So keep in mind this relationship of which acid is most strong and will expel or supplant any weaker acids from the caustic. Another couple of concepts that I want you to keep in mind, or a reference to be aware of, is there is another more theoretical YouTube video put on by BRE, and you can find that going to YouTube and looking in our Bryan Research and Engineering ProMax channel and our BRE 600 series. There is a webinar titled Caustic and Mercaptan Oxidation from June 2nd. And it's a very good video. It goes into more detail about the theory of caustic treating, and it focuses more on gas phase removal of species using caustic. And there's also a second webinar on this topic that we put on August 10th. And the video is not quite available on YouTube. It takes us a couple of weeks to get our videos up, or actually it looks like a little bit longer in this case. So that one's still waiting to be put up onto YouTube. We when it's available, you can find that one as well. But I find that in caustic treating, there are a couple of concepts that are necessary to understand, especially when we're trying to measure how much caustic is left available for utilization. And there's a concept called the percent spent of the caustic. And you'll never find a really definitive equation for percent spent for caustic. And I think the reason is because it's a percent spent based on what? Is it percent spent based on how much mercaptan is occupying the caustic? That would be a different equation than the one I'm showing here, which is the percent spent based on H2S capacity. So the fresh caustic, as it comes in, it doesn't have all of the sodium hydroxide is free sodium hydroxide. There's no acid bound to it. But as it contacts a stream that contains H2S, H2S will start occupying the sodiums and forming sodium bisulfide, the NaHS, or forming sodium sulfide, which is Na2S. As the sodium hydroxide is spent by being occupied by the sulfur species, there is the percent spent of the caustic rises. So every sodium can be, there's 2 sodiums that are needed to neutralize a sulfide molecule, and there's 1 sodium that's needed to neutralize a bisulfide molecule. So the percent spent can be calculated by looking at the ionic concentration of the sulfides times 2 plus the bisulfide, and then divide that by the sodium hydroxide in the solution. So this is a way that we will calculate the percent spent of H2S in one of the models we see later. And this is a concept that, if you're in a refinery, the percent spent of the caustic will be analyzed and reported, and you'll probably, discuss with operators, if you ever have this caustic treating unit, what is the percent spent of the caustic that you're using? Does it need to be changed out? When the percent spent reaches a certain level, such as maybe 50% spent, then you want to change out the caustic in one of these batch pre-wash systems. And we'll go over how that looks later on, but just keep in mind there is this calculation called percent spent for caustic that you need to be aware of, and this is how it looks if you're relating it to the amount of H2S that is occupying the caustic. And also, we're going to talk about the oxidation of mercaptans. There's a reaction that we need to be aware of. So at first, the caustic will grab the mercaptan from the hydrocarbon phase, but then there's a regeneration step where mercaptans are reacted with oxygen to form disulfides and water. And that is the reaction that removes the mercaptan from the stream, and it turns out the disulfides are insoluble in the caustic solution, so they will easily join or create their own second hydrocarbon phase, and that's how we remove the extracted mercaptans from the solvent to regenerate it. So just keep in mind there's this reaction where two mercaptans, the R stands for an alkyl group. It could be a methyl or an ethyl or a propyl, butyl. So those two of those react with oxygen to form a disulfide. So that's the most important reaction we're going to deal with in these simulations. So we're going to go over this exact simulation in detail. So this is the mercaptan removal from caustic using an extraction column. And basically the flow of this is that we have the LPG, or the hydrocarbon stream, that's exited probably a pre-wash vessel to remove any residual H2S. That enters this liquid-liquid extraction column at the bottom, and it'll rise, floats up to the top. And then fresh or lean caustic is fed to the top of the tower, and the caustic travels downward because it's heavier, and it picks up the mercaptans from the inlet stream and then becomes this rich caustic. So now we have this rich caustic stream. It's got mercaptans in it that it did not have before. We preheat it, we mix it with some air, and because that air, oxygen, is needed for this oxidation reactor, and then we pass it through a reactor, and this is just going to be a conversion reactor inside of ProMax, because this is a very complete reaction so long as you have enough air and sufficient amount of catalyst in the solution. And then we send this to a disulfide separator. We add some naphtha to provide a sufficient amount of hydrocarbon phase for extracting the disulfides into. And this is a three-phase separator. So we have some vent gas, we have this lighter disulfide oil stream, and then we have our regenerated caustic, and it is circulated back up to the very front end to enter the extraction vessel again. So that's the first case that we're going to look at. And then the second one is a very similar process, but instead of an extraction column that's used for instead of having an extraction column for the mass transfer between the caustic and the mercaptan-laden hydrocarbon stream, we're going to have two three-phase separators, or two liquid-liquid separators, that have the hydrocarbon flowing through in series, and then we're going to have the fresh caustic split from part of the fresh caustic will enter the first stage, and part of the fresh caustic will enter the second stage. And then the spent caustics drop out of the heavy liquid phases of both of these separators, and the sweet hydrocarbon exits out of the last separator as its lighter liquid phase. And then once again, you go through the same oxidative or mercaptan oxidation regeneration process, same thing. And then we have a considerably different type of simulation that we're going to look at, and this is a case where upstream of the Mirox units, the examples of which we've just seen, we have a vessel whose purpose is to remove any remaining H2S from the incoming stream, because, as I showed in the first slide, any H2S that gets into the regenerative mercaptan removal process, any H2S that happens to get in there is going to occupy caustic and spend it, and eventually you'll be extracting mercaptans with a caustic solution that is spent with H2S and will be no longer any any use for the caustic or the mercaptan extraction. So in this vessel, typically what happens is the vessel is partially filled with caustic, and then the partially treated hydrocarbon stream has probably come from an amine unit. The CO2, if there was any, and any the H2S should have been removed, but just as a extra layer of protection from H2S, we have this pre-wash vessel whose job is to remove the H2S, put it into this batch caustic holdup that's in this pre-wash vessel, and then over time, this caustic will get spent. And a common question we get is, well, if we have a composition of this hydrocarbon stream and we know that it typically has, say, for instance, 10 ppm of H2S in it, what is going to be the H2S concentration over time of the sweet LPG, and then what is going to be the pH and the percent spent of the caustic that is in this pre-wash vessel? So this is a dynamic problem. So we have to use a scenario tool to analyze something like this. And I'll show you how that works. But I will show you one result of this column, or of this pre-wash, because it's kind of interesting. Here we have a case where we have a small batch time, and we're showing the very early moments of a caustic pre-wash where the mercaptans are still being removed from the LPG before they have been supplanted by the H2S. So in this one, you'll see that the methyl mercaptan at very low batch times is removed from the LPG. So it's methyl mercaptan is going into the caustic, it's being removed from the LPG. But then as H2S enters the caustic, it's starting to push out. Less and less mercaptan is being extracted reacted into the caustic stream, and eventually you reach the LPG reaches a steady state value, which is the same as the inlet value of the mercaptan. So there's no more mercaptan removal after a pretty short time, and all that's changing in the caustic is that it's acquiring more and more H2S, and as that happens, the equilibrium will show that a little bit more and more H2S will appear in the sweet LPG. So on this other side, you can see that we're tracking the pH of the caustic as this happens, and then we're also tracking the percent spent of the caustic over time. So that's the purpose and the results, the key results that you're going to see by using the batch caustic pre-wash simulation. So we get quite a few requests for both the Mirox or Mirachem style unit for caustic or mercaptan extraction, and we also get quite a few requests to analyze the progress or the capacity of a caustic pre-wash vessel too. So these are in the caustic treating of LPGs in refineries or chemical plants. These are the common things that we encounter. So what I have tried to do, I'll switch from the sharing the PowerPoint now to switching to the ProMax simulation. Here's what we've done with the extractive mercaptan removal by caustic, or the mercaptan removal using the extraction column itself. The intent of this model is to be very, very easy for people to use. People who have existing or operating Mirox units, we want to send a model to people that they can adjust to match to their plant conditions very quickly. And I think this model does a very good job of that. You see here's the main process flow sheet. We have another flow sheet upstream, which is the feed prep flow sheet. So really the hard part of running this model is defining the feed composition of the hydrocarbon. And if we double click on this, we see that there is a hydrocarbon composition In this case, we have propylene, butane, isobutane, cis-2-butene, butadiene, NC5. So we have some hydrocarbons, okay? And then we're always going to have these mercaptans, methyl through butyl mercaptan. We're always going to have, in this case, we don't even have our sodium hydroxide yet. That's on the next flow sheet. We have the task that might happen differently from case to case is that your hydrocarbon composition might change. And it's not really too important to get your hydrocarbon concentration just right. You could be pretty good at simulating this if you just broke your hydrocarbon concentration down into C3, C4, C5, C6. If you made it that sparse, you could still do a good job of simulating this process because the propane and propylene aren't very different from each other in regards to how they behave in this extraction model. But this is what you would probably have to change if you want to match your plant's hydrocarbon concentration. You'd need to change the species that are in your environment, and you would then need to assign the hydrocarbon concentration. So if we go to the ProMax environment right here, the active environment will show the environment for this flow sheet. You can see that we're using the amine sweetening SRK environment, and we have this component list. There's a good chance that the next person who wants to use this template will want to change the species in this hydrocarbon layer. All of these hydrocarbon species, you would probably want to change those to match your plant's configuration. But I would caution you not to change any of the mercaptan or air and water, nitrogen, any of those, and sodium hydroxide. I wouldn't change any of those species in this environment. There's calculations tied to those that, if you remove those species from the environment, it would probably disrupt some of those calculations. So it's best to only modify the hydrocarbon species in your hydrocarbon feed stream. But once that's done, then all of the other changes that you want to make in this model are really done by just directly entering a value into these blue text boxes. These are user input boxes. You click on it, you change the value and hit enter. So now instead of having 1500 ppm of mercaptan, we have 1700 ppm of mercaptan. And I can execute this flow sheet. And now if we look into the extractor feed and we look at mass fraction basis on a ppm basis for methyl mercaptan, we see that it's 1697. So it's just within the tolerance of the solver that was trying to force this to 1700 ppm. That's what was happening there. So all the feed definition and feed conditions and composition definition is done on this flow sheet if you want to, but the same information is available on the second flow sheet. So really, you could, once you have your composition of your hydrocarbon established correctly, then anything else in this in this simulation are going to be modified simply by changing the values in these blue text boxes. So you can change everything in here by changing the values of these blue text boxes. I want to show the environment. In this case, I think it's different. I'm not sure I wanted it to be that way, but I believe it is. So yes, we have a different thermodynamic package we're using. We're using caustic treating SRK. And our composition list is changed because now we have, at least we have sodium hydroxide present now. And I know that wasn't there in the last one. We also have this oil called naphtha that is present. So those are things that are different from the flow sheet on the previous page, the environment for it. So, but now we have a very nice model where all we have to do is make changes through the blue text boxes on the user interface. So within a few minutes, you can, once you open this model and you know the information about your caustic treating unit, within a few minutes, you can enter the key information here and run the model, and you can start seeing what ProMax predicts to be the results. Like, so we know what the total mercaptans are entering this with the feed, and here we see the sum of the mercaptan or the resulting disulfides that are coming out, and we see also in the product we see the exiting mercaptans as well. So in this unit we've taken the mercaptan level from 1700 ppm and the total mass fraction of sulfur from 1141. Using this process, we've lowered that to 14 ppm of total sulfur. Now, in addition to the entries for process conditions, or key process conditions, we also have some recommendations. So for the first one I would like to talk about is the stoichiometric air to mercaptan ratio. So there's a certain amount of oxygen that's required to oxidize all of the mercaptan that are extracted into the rich caustic. And here is where we set what is the amount in addition to that we want to supply. So the typical range for the stoichiometric ratio of air to mercaptan is between 1.75 and 2.9. And so right now we have set this to 2.4. When you do that, that's going to automatically calculate the amount of air required to produce that stoichiometric ratio. So you don't set your air rate per se, you set your stoichiometric ratio, and then you have the right air rate. There's also another way of looking at it that's people will look at it sometimes as the standard cubic feet of air per pound of mercaptan. So that ratio is also something people want to see, and here is the recommended range for it, and we're inside of that. There is a recommended range for the temperature of the oxygen leaving the oxidizer, or the temperature of the contents exiting the oxidizer. We want that to be within a range. This happens to be a corrosion constraint. We don't want the temperature exceeding 120 degrees F for corrosion reasons. If you talk to a corrosion engineer, that corrosion engineer might say, keep this between 100 and 110 degrees F. And I see other places where they say, don't let it go over 120 degrees F, and definitely don't let it go over 140 degrees F. So there's varying comments about this, but I think this is the range that I would like to place on here. Your company may have different guidelines for that, but this is a corrosion related indicator. So the higher the temperature, the higher the corrosion rates get in this oxidizer and disulfide separator. There's also another corrosion related item, which is the percent of oxygen in the vent gas leaving this disulfide separator. So you don't want the oxygen content going over 12%. So they kind of like to keep it between 10 to 12%. But when you exceed 12%, you are raising the oxygen partial pressure to a range where it becomes corrosive in this vent line, and you want to stay below that. Then there is the caustic to hydrocarbon ratio expressed as a percentage. And for LPG systems, we like to keep this between 1 and 3%. We've got a little more than we need right here, it looks like. And for the naphtha gasoline range treating systems, you want to keep this caustic to hydrocarbon ratio between 10 and 20%. And then you can set the diameter of the tower, and we'll calculate the liquid load. There is a correlation called the Rocha correlation, which I use to calculate what I thought would be the maximum liquid load before you would encounter overcapacity of this extraction column. And those calculations said it would be around 100 meters per hour velocity in this system, or it's a liquid load. The units of liquid load are it's like gallons per minute per square feet. In this case, it's that calculation that has units of velocity. The Rocha calculation was doing everything in terms of meters per hour, so I converted those to meters per hour, and we're still very far below that in this case. And I don't have a high degree of confidence in this limit right here, so take that with a grain of salt. But this is a very nice model for letting you quickly set up to match your plant conditions, and then to see whether you're within recommended guideline ranges for these key performance indicators in the column. So I've got a couple of questions I want to get to that I've accumulated in the chat. So I want to read these for a second and then try to answer them. Yes, I have a good question about on the oxidizer stage. Don't you use a catalyst also? Yes, there is a catalyst. And I mentioned earlier that this oxidizer is configured to be a conversion reactor. And that is a good assumption to make, that we have a conversion reaction. So we're saying that we have these reactions where two butyl mercaptans and water, oxygen react to form this disulfide and water. So these are the reactions that we're using, and we're assuming that they all go to completion. And that is a good assumption to make, so long as you have sufficient catalyst in your circulating caustic solution. Now, we don't really model that catalyst and how much of it is present, and nobody really measures that. Everybody just performs a shake test on the circulating caustic to see if enough catalyst is present to oxidize any oxygen that's in the air that you shake into it. You take the rich caustic that has plenty of mercaptan, and you shake it, and you wait a certain amount of time to see if it changes color, indicating that the reaction occurred. And that's the way people find out if there is enough catalyst or not. So the amount of catalyst is never measured. It's a qualitative test to see if the amount of catalyst is sufficient. And it's just a liquid that you add into your circulating caustic. So it's just a liquid that's circulating along with the caustic. And whenever you find out that you don't pass the shake test, you add some caustic liquid to the solution and then go out and perform the test a little bit later on. But the model here assumes that there is sufficient catalyst circulating with the caustic, so that everything else about the reaction will be calculated properly. So you will see incomplete mercaptan oxidation if you do not have sufficient air. So if you were to bring this stoichiometric ratio to below 1, then you would see mercaptans that are not reacted in this oxidizer outlet stream. So that's something to note about the way the oxidizer works and the catalyst that is used. But yeah, there is a catalyst that is definitely used in this system, but it's not too hard to keep that catalyst at a sufficiently high level. So unless your caustic is just so black that you can't see the color change from the initial to the final color. I've seen that happen before. And I've got another question. There's a private question that says, please, why the C1, C2 mercaptans increase in molar concentration and then reach a plateau in a pretreatment, while the H2S only increases linearly? And I will discuss that question when we get to the simulation about the pre-wash, the batch caustic model. Okay, here is the the other common style of mercaptan removal system that we see. This is a very, very similar process. It's really the only difference that I can identify is that instead of there being a liquid-liquid extraction column, that equipment has been replaced by two liquid-liquid separators. And if you noticed in the liquid-liquid extraction column I showed earlier, there were only two ideal stages. So it's very similar to this because here we have, once again, two ideal stages. The difference, there's some special mass transfer equipment in these, which I assume are designed to make sure that they produce one ideal stage of separation in a smaller vessel than there would have been if you didn't have the special mass transfer devices in them. That's my assumption. I really don't know, but I think there's something in there to help mass transfer that's designed to reduce the size of these separators. And so instead of using a liquid-liquid extraction column that I think there's about 7 liquid-liquid extraction trays in a typical column, here you have 2 vessels, and you send part of your caustic to feed the first stage, and then that rich caustic is removed, and then you send part of your caustic to the second stage to treat the residual mercaptans, and that caustic is removed. So you have your caustic to hydrocarbon ratio overall is the same in this case as it was in the previous one. But since we're sending 50% to each stage, we really have 1/2 of that caustic to hydrocarbon ratio in each individual stage. I'm not sure how that really impacts things. I haven't studied it very closely, but this is really the key difference between the extractive distillation or the liquid-liquid extraction column process and the second process. So every single other thing is the same. Same parameters be entered through the spreadsheet. So there's really not much new to say about this one. To me, they're very similar, and they both provide about two ideal stages of contact between the hydrocarbon and the caustic, and that is about the extent of my knowledge on this. As far as I can tell, they have very, very similar, if not identical, oxidative regenerating process steps. Feed prep is also the same flow sheet we use for this. So if anybody knows anyone who's interested in simulating their mercaptan removal system, we are very interested in helping. We have very nice models that are designed for very easy use and easy view of your key process information. We'll be glad to help on these. And we do quite a bit of these. As you know, the mercaptan removal processes aren't really, they're not glamour processes in a refinery. Nobody, probably whoever, when I had one of these about 25 years ago, I spent a little bit of time on it, but I was, far more occupied with, the alkylation unit that I was covering. So I may have spent 98% of my time on the alkylation unit and very little time on this thing. So I think that's probably typical in the plant, but when this isn't working right, a process engineer is going to get lots of questions from the manager about this unit, and this is a very good, very easy way to acquaint yourself with your mercaptan removal system. Very quick, very easy. And that's what we all want, right? We want simulations to be very quick and very easy. And unfortunately, it's not that way often enough. Now proceed to the batch system. This is our simulation of basically a caustic pre-wash vessel. So there are, in this one, you still have to define your hydrocarbon composition, and that's going to change from system to system. So in your environment, you'll have to find what your hydrocarbon species distribution is, and put those species in here. And that's going to be more complicated in this model than it was for the mercaptan oxidation model, because not only do you have to, but what the extra complication comes from the fact that there is an Excel spreadsheet that I'm going to share now. You can see that there are columns for each component in your inlet composition. So in the environment, you've got these species. So I don't have very many here, but if you had more species, for instance, in your caustic pre-wash, than this ProMax scenario tool that is part of the Excel workbook, there is going to be more columns that need to be configured when you're trying to link your figure out what your Excel range is for the input and for the output of the caustic. So the scenario tool, if you change the environment in this simulation, you're going to have to change the number of, or the particular species in your environment. And once that's done, you're going to have to come into this Excel realm and add extra columns, put in the new names for all these compounds, and change the size of the range or the Excel range that's tied to the composition of your caustic stream. And what we do is we simulate. Let's get back to the ProMax view. We have to once you get your composition defined, and you're going to set your flow rate and conditions of your hydrocarbon feed. Once you do that, and I should have put blue. I didn't put the blue user input fields on this hydrocarbon input. I should have done that, but I should have done that for this flow rate and the temperature and the pressure, but I forgot. But after you do that, really what you're setting for each case is you're setting the caustic holdup, which is the inside of the pre-wash vessel. How many barrels of caustic are sitting in that pre-wash vessel during a given batch? So when you put fresh caustic in, you'll fill it up to a certain volume of caustic, and that number is what you need to enter right here in the caustic holdup. And then we want to look at the concentrations over time for a certain amount of time. We may say that we think that our batch is going to last for 20 days. So we want to run this and then watch over 20 days what happens to the concentration of the mercaptans as in the exiting LPG. So very initially there won't be enough H2S entering to spin the caustic and bring its pH down. So initially, you're going to see what looks to be, significant removal of mercaptans from your inlet hydrocarbon from your sweet to this caustic in the pre-wash vessel, so that you have less mercaptan in the LPG than you had coming in. So it looks like it's removing mercaptan initially, but as H2S continues to enter this system, the H2S will bind with this caustic, and whatever mercaptans were bound to the caustic in here will be expelled and sent back out with the next batches of sweet LPG. So eventually you're going to see your mercaptan levels here rise back to the same amounts that they were in the inlet. So initially, you might see very little, like 0% or 1% methyl mercaptan in your sweet LPG after the first time increment. But it won't take very long before the H2S entering the system is going to displace the mercaptan, and you'll see the mercaptan contents exiting be the same as the mercaptan contents entering. So it will no longer be useful for mercaptan removal once enough H2S has combined with the sodium hydroxide. So we have our initial caustic concentration, and when we set the batch size and the hold up time, that tells us what our initial flow rate of caustic is going to be. We use that to calculate the initial caustic flow rate. So when you make a change to either of these parameters or even any of these other inlet specifications, you need to run the model first. Let's say we're going to change this from 20 days down to 15 days. We're going to have a shorter batch time. So I'm going to reduce that. And I have to run the model first to load all of this correct information to properly initialize this start caustic stream. So we run the model once, and then we go to Excel and we open the scenario tool. And then we run this batch. So we're having time increments. The increment size is 0.75 days. That's based on the holdup and the holdup volume and the batch time, that and the fact that we have 20 increments that we're running through. So each of these time increments is 0.75 days. And we look at the caustic coming out and we copy this composition into this set of cells, and those are sent back into the simulation for the next time increment. So every time increment's caustic outlet composition is passed into the inlet for the next time increment, and this is repeated over and over and over. So as we go through the simulation, we are seeing the graph update showing our species concentration. This, after 0.75 days, we already had brought in enough H2S to completely displace any mercaptan that was in the caustic, before the first 0.75 days. So it didn't take long for all the mercaptan to be displaced. And now we're seeing the H2 level just rise and rise as more H2S enters the system and is being removed. And that H2S concentration is on the right-hand side axis. So we had an inlet composition of 50 ppm of H2S. And you can see in the pre-wash that, still some H2S is getting through. So even though you had 50 coming in, you need to decide what is the maximum amount that you're content with entering your mercaptan removal system, and that's gonna eventually spend the caustic in that system, and causing over a long period of time you to have to change out your caustic system there. So, here you have more frequent and simpler change outs of caustic that are the more frequently you do that change out, the less often you're going to have to change out the caustic in your regenerative caustic system for mercaptan removal. Appreciate you spending your time to listen to this talk. I hope you enjoyed it. Hope you found it useful. And we are, very interested in helping anyone who would like to study their own mercaptan removal systems.